Okay, so now that we kind of have a good sense of putting these into matrix form by hand, thinking about it in a different way to be able to do this computationally. So I went back down to a two-spin system to simplify this. I'm going to go ahead and solve this again real quick. I know we've kind of gone through this a few times already, but I want to do this um, thinking about things in binary versus up arrows and down arrows. Um, so we're going to have our four basis states here. We're going to have 0, 0, which would have been like down, down, let's say. We'll have 0, 1, we'll have 1, 0, and we'll have 1, 1. So that's going to be our four basis states. Our matrix is going to be, we can call it 0, 0, 0, 1, 1, 0, and 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. Okay. And if you solve this real quick, so 0, 0, so let's say that's down, down. So we're going to have h bar squared over 4 with 0, 0. And then nothing else because we can't lower a 0. So here we're going to have, so we have opposites here. So we're going to have a negative h bar squared over 4. And then we're going to have our, so our original, that's going to be our SZ operators. But then we're going to have a plus h bar over 2, and then the flipped state, 1, 0. And if you got enough practice with, so I kind of skipped a couple steps there, setting one of these to 0 and using one or the other. But if you did enough of these in the 3-spin system example I had in my last video, you kind of get the pattern of that. So anyway, so then that's going to be it for that one. Then this is going to be, again, negative h bar squared over 4 with 1, 0, keeping the state the same, plus h bar over 2, and then the flipped state, which is going to be 0, 1. And lastly, we're just going to get h bar squared over 4 with our original state, 1, 1. All right, so we put this matrix together real quick. We've got 0, 0. So let's go ahead and factor out this h bar squared. So then here in 0, 0, we've got 1/4, and then 0 the rest of the way. No other matches. For 0, 1, we've got a match here for 0, 1. So nothing for 0, 0. We have a match for 0, 1. We have negative 1/4. Then we have a match here for 1, 0, positive 1/2. And then nothing else. For this one here, we have negative 1/4 at the 1, 0. We have positive 1/2 at the 0, 1. And zeros for the rest. And lastly, we have 1/4 positive. All right, so that's our matrix for our two-spin system right there. So now let's see if we can figure out some patterns. First of all, we see we have plus 1/4 on the corners with the rest zeros. So that's something. But let's go ahead and say we're going to loop through each column. So let's have a variable named a, and it's going to be the value for each column. So the first iteration of the loop, we're going to have a is equal to 0. So this is going to be loop number 1, and then loop number 2, a is going to be equal to 1, and then a is equal to 2, and then a is equal to 3 for our third iteration of the loop. So our first iteration of the loop, we know that we want this here, we want the point 0, 0, we can call it, to be equal to 1/4. Or we can call this AA. So AA, in this case, is going to be 1/4, first iteration of the loop. So for this one, so AA here, which is going to be 1, 1, is going to be negative 1/4. And here, AA, which is 2, 2, which is also negative 1/4. And AA here is going to be right here, positive 1/4. Okay, so what do we got here so far? Not an exact pattern because we got some things changing here. But if we write these in binary here, so this is 0, 0, this is 0, 1, 1, 0, and 1, 1. So one thing that we can see is that if the bits are the same, then it's going to be positive 1/4. If it's different, it's going to be negative 1/4. And that's something that will hold true for higher spin systems, with the 3-spin systems, 5-spin systems, and so on. But we can see for our the samesies, our 0 zeros and 1 ones, we're done. So once we have the 1/4, the rest of them are zeros. But for the other ones, we're not done. We do get the negative 1/4 on the diagonal, but then we also have this other one here. So let's take this one for example. So we have our 0, 1, and then so this is going to be, so this is going to be, so 0, 1, 0, 1. So this is the point 1, 1. So this is going to be the point 1, 2. So the point 1, 2 is going to be equal to, I'll get back to that. Point 1, 2 is going to be equal to positive 1/2. All right, so point 1, 2 could also be called, well, let's do that in binary. So let's do 1, 2 equals 1/2. All right, and you can see that that is the flipped version of our A. So really what we have is A, and we have, we'll call it a function named flip. Pass A into the function called flip, and then that's going to be equal to 1/2. So A with flipped A is going to be equal to 1/2. So we're going to have the combination of the two things. We're going to have, first of all, our AA. This is with the assumption, like for, I'll write this over here, for, I'll call it A0 and A1, where A0 not equal to A1. I'll say if, because for implies a for loop. We're not doing a loop here. If A0 is not equal to A1, first of all, we know that we'll call our end result, this matrix here, we'll call this a multi-dimensional array, H, and it's going to be a multi-dimensional array. So yeah, we'll call it H. So first of all, we know that H A is going to be equal to negative 1/4. And then we know that H A flip A is going to be equal to positive 1/2. All right, so we kind of got our little mini function there. Else, so if A0 is equal to A1, then all we need to do is this part right here, which is going to be H A equal to positive 1/4. So we have the two cases. If the bits are the same, we go here. If the bits are different, then we have to do this here. All right, and then so this will get you by. This is the majority of the logic here for a 2-spin system. And really, adding additional spins isn't really that much different. All you need to do is do a loop through each of the sets of spins. So basically, if there are 3 spins, you would loop, we'll call it n-1 times. So because there's 2 spins, we only need to do this a single time. If there were 3 spins, then we need to do it 2 times. So if we have a spin 0, 0, 0, any 3 spins here. So the first one would be 1 and 2. So our first iteration of the loop, and we can call this I. So I is going to be 0 starting off, is going to be the first spin, and then we can create another one. So I, for the first iteration of the loop, will be equal to 0. Hopefully this isn't too confusing. Then we can create a new variable called j, which is going to just be I plus 1, which for the first iteration of the loop will be 1. So going through this the first time, we're going to, instead of saying 0 and 1, we would say I and j. Because so then we could compare the two spins that are side by side. So the first iteration of this little inner loop here is going to be the first 2 spins, and then you get through that and you do the second 2 spins. So then I would be 1, and then j would be 2. So 1 and 2 right there. To do that the second time. So that's really the only difference moving up in number of spins, is adding that loop there to go through each set of spins. And you wouldn't want to do the final spin because If you try to set that to I, there is no I plus 1 at that point. So you'd want to stop. The last one that you do would want to be that second to last spin. If you want to try that. But I'd say, first of all, try to get this code working for a 2-spin system to see if you can come up with these values right here.